with that, let me move on to the next short channel effect, which is known as drain induced barrier lowering. DIBL, okay. So this is the effect that I was talking about yesterday, where because of this depletion region eating into your channel, the threshold voltage also changes, okay. Now, so let us look at this. N plus P okay, and this is my source, drain, body, grounding these two, VG and my VD. So in a long channel device, if I changed my drain voltage from say 50 millivolt or 0.1 VDD to VDD, let's say there is a technology where there is some VDD given to you. If VD1 VDS1 equals 0.1 VDD and VDS2 equals VDD, and then I find out what the threshold voltage of this transistor is. And how do I find out what the threshold voltage is? I have to increase my gate voltage so that that surface potential is developed in whatever particular way, right, as per that definition, right. Are these two threshold voltages expected to be the same or different? Same. If it's a long channel device, you saw the expressions that we derived, it had no dependence on VDS, right, which is quite understandable. And the reason for that is, of course, this depletion region is sitting here, okay. Now this depletion region's width or length, right, or the depth of this depletion region doesn't go far into the channel, so therefore it's negligible and the effect of this VDS is not seen on the threshold voltage. Of course, now if I bring this really close, right, and make a short channel device like this, N plus, then this depletion region can look like this when VDS equals VDD, right, and look like this if VDS equals 0.1 VDD, okay. Of course, now because this, of course, by the way, here my gate is only till here because it's a short channel device. I have moved the drain from there till here, right, short channel device. Now, of course, it is true that because the depletion region has gone far into the channel, right, I have been able to generate some depleted charge carriers here already, which means part of the channel has already got depleted because of my drain voltage that I have applied. The gate has not yet done anything, okay. Now if I start ramping up the gate voltage, the gate has to deplete only so much of the channel, right. On the other hand, if VDS was 0.1 VDD, then the gate would have to deplete all the way till here, right. There is more part of the channel that it has to deplete. Therefore, which threshold voltage do you think is going to be higher? 0.1 VDD, it has to do more work and therefore that has to be. Now, if VDS is very small, okay, and VGS is fixed, right, let's say, what region of operation is the transistor in? If VDS is very small, VGS is quite large, linear region, right. Therefore, the threshold voltage corresponding to this region, right, VTH is called VT lin, threshold voltage of the transistor in the linear region of operation, and this obviously is called VTH is called VT sat. For long channel devices, VT sat equal to VT lin, but for short channel devices these two numbers are different, and they are different because of the intuitive explanation I gave you, and that is called drain induced barrier lowering. Okay, so the Dibble coefficient is my VT lin minus VT sat divided by whatever my VDS, whatever voltage I applied on the drain for the saturation region. Let me call that VDD, and this is 0.1 VDD. Okay, the threshold voltage gets altered because of this. So the VTH will become like VTH naught plus gamma times root of VSB plus psi s minus mod psi s, right? What should happen now? Suppose I call this as eta. How should this thing change? Should it be plus? Should it be plus, or we'll put the sign later, eta times VDS, right? Ultimately it's a VDS. The drain voltage is inducing a barrier lowering, right? And it's barrier because the energy bands actually drop, lowering the barrier, allowing more electrons to go through and all that. So what should be the sign here? It should be negative. Threshold voltage should decrease if my VDS increases. Okay? Yeah. 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 I am just saying that no, what I am saying is by long channel definition itself, all these changes are negligible. Of course it does happen, what you are saying is true, but that eta coefficient will be so small that it won't really affect your value, that's all. Okay. Yeah. So now this actually is not a good thing, by the way. Okay, even though the threshold voltage actually comes down, it means your current goes up. You may think, well, that's a great thing, right? I can get more current out of the transistor, but this is not a controlled way of doing it, and therefore which also means that you will have more leakage, which I'll talk about later. You will have more leakage current, which is again not a good thing. So therefore you have to do something to control this particular phenomenon of Dibble. So what do people do? So we will go and invoke our PN junction idea that we had discussed, right? We discussed about 3 ideas. So N plus P again my gate and oxide and all that. So what was the problem? My problem was my depletion region was actually going into the channel like this. And why was that happening? Because this is an N plus P junction. So VD, VG, right? Body is grounded, VD is a positive voltage, and therefore that's a reverse bias junction, and that is going in. Now the problem is because it's n plus p, the depletion actually penetrates farther into the p than into the n plus, right? So just think about this. You add what is known as an p plus halo implant here. This is a p plus halo implant. Okay. Now what will happen? I apply VDS, but because this is p plus and an n plus junction, now the depletion region will penetrate further into the n plus than the previous case, right? So effectively, if this was my earlier depletion region that was formed, now it would simply come down to, let me use blue, it would come down to this, because the p plus is there just near that diffusion region, right? Of course, earlier if my depletion region in n plus was still here, now it will go in further, it will go in all the way till here, effectively. So what we are saying is, it doesn't matter if you penetrate into the n plus region, don't penetrate into the channel. That is the intuition behind a halo implant. Okay. Now the question is it enough if I do this only on the drain side? Why? Yeah? Leave it. Yeah. But the catch is, physically if you look at this structure of a transistor, they are actually reversible terminals. In fact, unless if you give me just a transistor and ask me and give me two diffusions and say which is drain and which is source, I'll say I don't know. You have to tell me what potentials you applied where. That's what determines what is the drain, what is the source. Current will always flow from a high potential to a low potential. So therefore, the one on the higher potential for an NMOS transistor is the drain, the other potential is the source. Now, in my circuit, I could well reverse these two voltages, have VD applied here and ground that end. So therefore, I need to do this on both ends. Structurally, they are the same. Okay, in a BJT, for example, this is not how it is. Physically, it's different. So I cannot actually swap the emitter and collector. It is defined physically and in only one way. Whereas for a NMOS transistor, that's not true. Okay. So this now brings us to what is known as dependence of VT on channel length. So if channel length is long, what will happen to the VT? Yeah, it's basically a constant. It will be like this. Now, which short channel effects coming in, right? Basically, which means that I am having this depletion region eating into the channel. Then what will happen to the threshold voltage as I reduce the channel length? It has to decrease. So this is what will happen. Of course, we have not captured this in our threshold voltage equation completely. Okay. So it's very complex, and that's why that model file that you saw yesterday had 54 parameters in them to capture all these effects somehow. Okay, so this is basically the short channel effect. Now, because of this halo implant, to avoid this dibble, we put some halo and did something. What should happen to the threshold voltage there? It will actually go up, because now the bulk is not just P, part of it is P plus, right? So the threshold voltage, if you remember threshold voltage, it goes as square root of Na. That Na concentration has gone up in some regions. Okay, so therefore threshold voltage will go up. This is called reverse short channel effect. Because of the halo implant, it will go up a little bit, and of course after that it has to come down. Because beyond the point, if you make the channel length so small, your depletion region will start eating into the channel eventually, right? So this is called reverse short channel effect. Or this is the effect of the halo implant that we have put in the drain and source end of the transistor. Okay.